Welcome to this Making Pharmaceuticals Digital Week webinar. My name is Vicky Chapman and I'm the event manager for the Making Pharmaceuticals exhibition and conference. Please do visit the makingpharma.digital website, www.makingpharma.digital, where you'll find information about the online hub, a section on white papers and links to other webinars which we've already run. The on-demand files for Digital Week webinars will be available on here from the 3rd of November. This webinar is from the Process Engineering and Formulation Focus Group, Academy of Pharmaceutical Sciences, and the speakers are Dr. Kendall Pitt from GSK and Professor Zishan Ahmed from the Leicester School of Pharmacy, De Montfort University. Kendall will be discussing manufacturing classification system, putting numbers to tablet development. And Zishan will present electrically driven emerging technologies for the manufacture of pharmaceutical dosages. The speakers will be taking questions at the end of the presentation via the question and answer function, so please do use the question and answer function throughout the presentation and we will answer all questions at the end. I'd like to hand over to Kendall. Thank you.
Thank you, Vicky. Can you hear me?
Yes, I can. Thank you.
Thank you very much. So good morning, everybody. My name's Kendall Pitt, and I'll be talking about the manufacturing classification system, putting numbers to tablet development. The manufacturer classification system, the way to look at it is a way of logically selecting manufacturing processes for oral solid dose based upon the properties and material that you have. Now, my daytime job is that I work in manufacturing at GSK. I'm part of the technical group at manufacturing. One of my hobbies, though, is being the co-chair of the Academy of Pharmaceutical Sciences Process Engineering and Product Formulation Group. So you want to find out more about the Academy of Pharmaceutical Sciences? Do you want to join us, help organise events? Because we're here to basically advance science and technology within the pharmaceutical sciences. So if you want to find out more, Google APS.org. Normally I do this face-to-face and talk to people, but to make this a bit more interactive, we'll start with a poll. So I will ask you a question now about what you know about the manufacturing classification system. So Vicky, could you pull up the poll? So you should see a question: are you using the manufacturing classification system in your company? And you've got 5 options. So just select one of those by dabbing your finger at the screen or clicking on your mouse. I will give you a couple of seconds or so to vote. So thanks. Thanks. Vicky, can you bring up the poll? That's quite interesting because we've asked this question a number of times on this, and we get more people down towards the bottom, which is we don't use it at all, or in some cases we haven't heard of it. So I'll talk a bit more about it today to give you some idea of what we're doing and why it works. And interesting that some people are actually moving it. Next slide, please. Yeah, if you look at the tableting process, what you have on the left-hand side is you have the drug, the excipients, then a black box, some magic happens, and then at the other end, you get a tablet. And what we're trying to do with manufacturing classification systems, demystify this selection bit in the black box. What is it about your materials which you may want to use and select to actually make you design your manufacturing process properly, be it a dry process or a wet process or a more specialized process? Click, please. If you look at these 2 pictures here, which are calcium sulfate or gypsum, this gives you some idea of what we're trying to get at. Now, these are chemically the same material, but clearly they're completely different particles. One on the left-hand side is down to about 2 or 3 millimeters inside, and the one on the right-hand side is an enormously long calcium sulfate crystal. It's one which is actually grown in one of the caves in Mexico. And you just about see a man down there. So clearly, these have got completely different sizes, completely different shapes, completely different properties. So the take-home message from this is, when you're ordering or looking at drugs, for example, don't just look at what the chemical analysis says. You've got to think a bit more if you want to process these things. What's the size, the shape, the surface area, or any of these other things? Thanks. Next slide, please. This is a whole range of tableting issues. I won't go through all of them, but these are sorts of things which you might see, and these are things we're trying to avoid by selectively getting the right process for manufacture on that. So you've got the things like capping, lamination, cracking. Some of these, if you carefully design your processes, then these shouldn't happen at all on that. Next slide, please. So if you start looking at this from a perspective of what is good and what is bad, this is a selection of photos of different active pharmaceutical ingredients. And these have been classified as being difficult. If you look at them, they are sort of looking quite ugly, aren't they, really? They're very, very fine particles, there's needles, there's fluffy material. Some looks a bit like hay ricks on the bottom right-hand corner. So they look by eye quite ugly. If you go on to the next slide, please. If you look at this slide here, this has been classified as good API. It flows, it compresses well. As you can see, that they do look quite beautiful in some way, in the sense they're nice and ordered, they're clumped, they're a reasonable size. You can just about see that there's distance bars at the bottom. So you can see these are about 50 to 100 microns. So the key about this is if you can by eye tell a difference between what looks good and bad, then you're getting into regimes of artificial intelligence and training systems and putting numbers down so that you can then do this automatically. You don't have to just guess. You can put rules in place as to what looks good and what looks bad. So the next slide, please. So the manufacturing system, when we approached and started thinking about this, we decided to use the style of the biopharmaceutics classification system. I'll quickly just talk you through this on this. And what you can see on the biopharmaceutics classification system, you've got an axis on the left-hand side, you've got how well the drug is absorbed, and on the bottom axis, you've got how soluble the drug is, with the far right being insoluble. You can see that you can start putting numbers 1, 2, 3, 4. You can start seeing that bright green is what you'd ideally like to have, and red is not what you really like. So really, if we're actually looking at a drug from its molecular point of view, rather than its particulate point of view, from the molecular, you want it to be highly permeable and highly soluble in a nice green zone. You don't really want ones down in the low permeable and low solubility. The area which is perhaps the most interesting if you're a formulator or manufacturing is the 2 zone, which is highly permeable and low solubility. The reason that I bring that out as an example is you see a reference there to the development classification system underneath by Butler and Dresman. If you're a formulator or in manufacturing, you can start controlling the absorption of your drug by just controlling the particle size for those type 2 drugs. I say read those papers below, but you've got the general theme here that we're looking for a system which is red, amber, green. Green we like, we can change things quite readily. Red is probably a bit more difficult. Next slide, please. So why would you bother a manufacturing classification system? We're trying to assist rapid development and changes and using minimum resource. So we're trying to give guidance to people about what defines a right particle and what's the best process. We're also setting target for engineering, that's particle engineering, crystallite people, as to what we need to get a good API. I use it quite extensively in development and subsequent transfer for manufacturing. As processes progress through their life program, that is for after initial launch, you'll find that you'll start changing your API. And this gives you an idea of your sources of your API. And this will help you understand what you can and cannot change readily. Gives you an understanding of risk. Simple terms, we talked about traffic lights, red, amber, green. Green, you can make lots of changes in that particular region without any problems. Red, you might. In reality, there's a little gradation across like a spectrum, but it gives you some idea of that. And it fits with quality by design principles. When I talk about QBD, if you've not heard it, it's got lots of definitions. I like the one that it's just good science and common sense. That if you're applying good science and common sense, then your products will work and your formulations will work well. We're also looking at pushing forward regulatory relief to see if you could classify your materials as being in the green zone, you might well get relief as far as filing any changes later on. on that. Next slide, please. So how do we go about setting up this manufacturing classification system? Well, we had a meeting. It was under the Academy of Pharmaceutical Sciences. It seems it's actually quite a long time ago now. It's 2013 at University of Nottingham. And what we did is we assembled people, breakout sessions. We asked people, if you were a synthetic chemist, what would you be interested in from a particle perspective? If you're an analytical chemist, what would you want? If you're a formulator, and sort of grossly over-exaggerating results. But what you tended to find is that if it's a synthetic chemist, they were just mainly interested in the purity. Analytical chemists wanted a chromophore in the product. Biopharmaceuticals people wanted it absorbed, and manufacturing people wanted it to flow and to be able to compress. So we then started putting rules and some guidances around those concepts to come up with a classification system. Next slide, please. Now, we were helped to a certain extent because we were able to pull upon some existing literature. This is one from Bruno Hancock's group back in 2004 at Pfizer. And it talks about what the ideal parts for a direct compression. And there's a list of things like size, blend uniformity, flow, compression. And so you can see we then, in the same slide, also put together this concept of a gradation, whereby if it's an easy particle, if it flows well, you consider direct compression. If it's got some concerns, you dry granulate, wet granulate if it's difficult, and then you've got the other technologies where you need to think very carefully about what the changes you are. So next slide, please. So we're all on the same page, you've got the same thoughts. This is a standardization of what direct compression is. So you particle size or grind a drug, you blend it, and then you compress it. Now, this is clearly the most economical way to proceed. It's very simple in the sense that there's only one or two steps in it. But what you're highly dependent upon are your API properties. They've got to be able to flow, they've got to be able to compress, and they mustn't segregate. So very easy systems to run if you get a good API. But what if your API properties change slightly? So that's a basic overview of direct compression. Moving on to the next slide. Next slide, please. This is dry granulation or roller compaction. Here you are grinding the drug, you're mixing with excipients, then you roller compact it into usually into a ribbon, then you grind it again, and then you mix again, extra granular excipients, and compress. So you may well ask, well, what are you doing here? But typically your input drug at the start is very fine material. You may well be below 50 microns in size. When you've roller compacted it into a ribbon and then milled it again, you're typically more like 1,000 microns, 750, 1,000 micron size, typical size you come at. So you've increased your particle size from 50 microns, which doesn't tend to flow very well, or below 50, to something which is usable. Chemical engineers tend to like this, ODU manufacturing people, because there's lots of knobs and dials and things you can change. So if your API changes early on at the start in the grinding of the drug state, or prior to that in synthesis, you've got some opportunity to change its properties before you have to make tablets from it. Next slide, please. This is wet granulation. In this case, you're grinding the drug, you're blending it, you're then applying solution onto it, usually water. You're sieving it, drying it, sieving it again, and then blending it through. Some people refer to this as a chemical torture for the API. To get it through this, you've got to have something which is both stable to water and also stable to heat. And you're also possibly changing its form as well. So you need to think carefully about wet granulation, reserve that for special cases. So next slide, please. So the output from these deliberations at Nottingham and the discussion of bits and pieces was a paper, manufacturer classification paper. You can readily download this off the internet. You need to possibly, it was by Michael Lean, myself, Gavin Reynolds, and some other group of people. I suggest you Google my name and Gavin's name, Gavin Reynolds' name, because there's a singer called Michael Lean, so you get about 6 pages of his songs before you get to this paper. So just Google myself and Gavin's and you'll get up the paper. Part of this was interactive, was a questionnaire. So we're going to stop and have the second poll now. Second poll will be, what do you consider to be important? So It's come up. So what material properties do you think are important in a selection or manufacturing process? Is it size, shape, surface area, surface energy? So you know what to do. Jab your fingers at the screen or click, and you can pick a number of those if you like. So I'll give you a few seconds to do that. Thanks. Okay, here we have, it's interesting. So it's interesting that quite a lot of you have gone for the size and shape, surface area, and surface energy. It's quite interesting to see how that is. You can see the importance of the things which we looked at. Now, as I said, we actually did this early on in the development of this program, and I'll now show you the slides, sorry, next slide, which shows the results of the people who responded back to the paper. The questions are slightly different, but you still see that size and shape are ranked as quite high on that, and then surface area are a bit lower. But it's interesting, it's the size and shape part of that. So it's okay having this decision that these are what are important. What are you going to do about measuring this? What can you do? Next slide, please. One way of looking at this, sorry, can you open all the question all the way down? Sorry, shouldn't have it build in that. So yeah, these are the sort of measurements which we then went out and asked people to check. So particle size, we asked to look at 50%, what's 50% by size, what's 10%, 90%. Particle shape, circularity, if it's a round soccer ball, then it's circularity of 1. If it's a rugby ball, then it's 2. If it's like spaghetti, it's particle shape about 10. Compression, we were looking at the mechanical strength of the particles. Flow, we were using car index, and dynamic vapor absorption. These are ideas which we put out. This is sometimes referred to as the FIP friendly list, which is the Federation of International Pharmaceutical Societies. Anyone can do these at minimal cost. I work in manufacturing. If those also work in manufacturing, we know that money is always hard. All the money has been given to R&D to gamble on new products. So we get a lot of money, but we can get all our sites doing this very easily with virtually very little equipment if we have to, bearing in mind GSK operates worldwide around the globe. Some interesting quotes. This you can do it in minimal list. Something to think about: no product should fail from a predictable reason. If you look at some of these rules and some of the suggestions there, then you can start rethinking, well, we should never have done wet granulation, or we should have done direct compression. The other part of this of taking these measurements is none of us have infinite resource. So this gives you some idea. If you take these measurements of what further areas do you need to concentrate on? Is electrostatics going to be an issue for you, for example? It's something you need to do on that. So I'll give you some quick examples of this and ones that you used. Next slide, please. This is particle size and shape. This is what you can do with a USB microscope. They're typically £30 or so. You just Google them off the internet. They might be getting a bit cheaper as we're getting towards Black Friday. And ImageJ software. And this happens to be Beecham's powders. And you can see you can very quickly, with these very simple £20 microscopes, which are attached to your laptop, you can see size and shape. You can do that, and you can also do some identifications on there as well. Those skilled in the art, the one with the 50 or 0.15 millimeters, the paracetamol particle, and just to the south of it, that triangular shaped particle is lactose. That's your lactose tomahawk for those who want to look at particle sizes and numbering. So you can see you can do this quite easily. Next slide, please. The other thing we tend to record is the mechanical strength of compacts. I'm usually told the fact that if you put an equation up, about 50% of the audience drop off. So hopefully there's slightly more than 25 of you left now on the call. But you can see it's an equation. What it does, it's the 2p. The 2p is your fracture load, or your hardness. D is diameter, T is the thickness. So it actually takes out the size effects of your tablet. The bigger the tablet, the bigger the fracture load should be. But you get a target. If you solve that equation, it comes to 2 megapascals. And that's sort of the goal, people out there. If you can look at it as your leisure, because it's in USP Pharmacopoeia and European Pharmacopoeia under those monographs. So you can look at that as well. Next slide, please. Again, flow, you can use complicated systems like shear cells, but the usual easiest way is just to use compressibility car index. And this is an example of ranking what future work you may need to consider. In the car index, you fill your measuring cylinder with powder, tip it end over end, get one volume, and then you tap it down and get another volume, and the difference gives you an idea of the flowability. So the more it collapses, the poorer the flow. So you see in this thing here, you've got a green zone where if you've got these car indexes of 20%, you should have no real issues in scale up in manufacturing. It should come out of all your hoppers, should be able to move it around on screw augers and things like that. The amber zone is probably the interesting zone. This is an example you probably need to do more work because it will get stuck at some point, these powders, if they're 21 to 25% car index. And you could even Google and Wikipedia this, and it will tell you you will have problems with these sort of powders. So it probably means you need to think about your equipment. And then the red zone is where you definitely will have problems in flow. You will be around to that GMP mallet coming out to hit the sides of a hopper, GMP sticks I've seen used as well. There will be issues with those. And that sort of gives you the guidance of what future work you may need to do or what formulation work you need to do to get around that. Next slide, please. This is an interesting example of when we're looking at surface energy or looking at absorption. In this case, along the bottom, we've got the percentage RH of the air that you are in. And on the y-axis, the vertical axis, you've got how much water has been taken up. If you have lots of money, you use gravimetric volumetric GVS systems, or you haven't got money, you use a desiccator or glass jar on the left and start weighing the powders individually. But you can see that there's clearly two populations here. There's one along the bottom, which doesn't pick up moisture, and there's a particular example which does pick up a lot of moisture. And if you look at European Pharmacopoeia definitions, the one which is on the blue at the top is shown as being slightly hygroscopic. So what was interesting in this particular example, if you go to the next slide, please, you'll see that on this side, we've got a compaction pressure. That's a pressure we use to form the compact. And on the vertical axis, we've got the tensile strength, the magic 2 sitting there. What you can see is a slightly hygroscopic one is actually gave us higher mechanical strength tablets. This is where we were thinking about, well, what is this? It's possibly something to do with surface energy. The more higher the surface energy, the more moisture it's going to pick up, and so also the more surface energy it's got, it's probably going to be form bonds better. The upside of this was that the slightly hygroscopic one was actually the better product to take forward and actually form tablets a lot better. Next slide, please. Part of the manufacturing classification systems to help you make decisions and project things in a nice orderly manner. I quite like this picture here, where the black line is that of one particular salt form or crystal, and the blue is another. Along the bottom, we've put together some of the biopharmaceutic systems, some of the manufacturing. So you've got dissolution along the bottom, you've got flowability in the next bracket, you've got content uniformity and manufacturability. And we put an attempt to put low, medium, high risk. If you still look at the slides or look at paper 1, you'll see the actual numbers at top and bottom are fairly realistic of what you'd expect. So what you would see from this is that by a long way, the blue line is probably the best one on all areas of absorption, manufacturing. The black line probably isn't, but you're probably going to find that because of the pharmacology, you'll be given, you won't have much choice which one you select. But if you end with a black one, you then know that you're going to need to look at flowability. Final slide, please, on this. I've been through this fairly quickly. This is the last paper, which is paper 2. This is very much a team effort in developing this product and this concept along. By all means, look at the papers, come back with suggestions, and if you want to join the team, then contact any of the authors up the top there, and we're more than willingly bring you in.
Perfect. Thank you very much, both of you, Kendall and Zishan, for those presentations. I think they were so interesting. I think we've got a couple of questions actually from the audience. So we've got, I believe this is a question for you, Kendall. Dean has asked, could the MCS be used for continuous processing?
Thanks. That's a very good question. In the second paper, we do briefly touch on continuous processing and MCS. What I say to people is a good example is wet granulation. If you're making that, you're usually wet granulating because the API doesn't flow very well. So if you then start wanting to make something continuous, it's got to flow. So you do need to think carefully about what you're doing. So when you're talking about continuous, is it continuous wet, continuous direct compression, or continuous roller compaction? And then thinking through what are you really interested in? But absolutely, it would lend itself to continuous processing. Thanks.
Fantastic. And another one for you, I believe, Kendall. Jamie has asked, can the MCS be used for excipients?
Yeah, again, a very good question. One of our co-authors, which is Peter Kleinbutter, has actually started looking at excipients. And again, picking a neutral topic such as mannitol, for example. On some conditions, you may well want the mannitol, which has got the property of icing sugar, very lumpy, you can mold it readily, as opposed to the mannitol, which is very free-flowing and granulated. That would be a roller compaction direct compression grade. So absolutely the same thought processes which are being used for the active pharmaceutical ingredient can also be used for excipient. So good question, thanks.
Perfect, thank you very much. We have a question for Professor Ahmed, so Zishan. So from Yash, apologies if I say any of these words incorrectly. Coaxial electrospray in formulation used into finishing, such as possible oral form, etc. Is this a patent technology of university, I wondered?
So we do know that there's a lot of work currently going on with these types of technologies and a lot of explorations. So some of these are actually, you cannot patent them because of a change in the materials, but we have seen a lot of preparation of oral dosage forms. So I don't know if it's been patented or not. We're kind of like working on different types of patents, but not necessarily on solid oral dosage forms. So that's the very short answer there. It's open for discussion if Yash would like later on.
He has a follow-up, I believe it's a follow-up question. Have you tried this technology, for example, in reduction in usual paracetamol dosage of 500 milligrams to lesser value because of immediate delivery?
Yash, we have not tried that. We're trying some other sorts of things at the moment, but it is something that can definitely be done 100% because we've shown already that we can manipulate the release of active from these structures, and actually we could delay the release as well. So it's a very valuable technology. We've noted that down in lots of our grants. But yeah, again, that is open to discussion if you'd like.
Fantastic, thank you very much.
Yeah,
that's all. Oh, sorry, Kendall.
So I'll just build on that last response by Zishan there about what you can do. You've got to think about your therapeutic indication and what you want to do. So, for example, some people want a migraine, for example, you need to get it in as quickly as you can. So if you've got a drug which you want to get in as quickly as you can, then coaxial would be definitely the way to go. If it's a rate of onset is absolutely vital, then these are sort of technologies to think about rather than waiting for it to be orally absorbed on that. But yes, thanks.
Fantastic. It looks, oh, sorry, we've got one more question. I think we'll just about have time. Ali has asked, what has been regulatory feedback on MCS?
It's actually in Japan has been very positive on this. We are presenting this in Japan and they quite like the idea. The rest of Europe has been a bit distracted on COVID, but definitely Japan like this approach of the MCS. So the Japanese like it, but I'm sure we'll follow. Thank you.
Fantastic. If anyone has any more questions, please feel free to contact our speakers. But for now, please do visit makingpharma.digital, where you'll find information about the online hub, a section on white papers, and links to the on-demand files for the webinars, this one will also be on there after Tuesday next week. Thank you very much to Dr. Kendall and to Professor Zishan, and thank you for watching this Digital Week webinar. Thank you.
Thank you.
Bye.